Electronic Specifier.
Welcome to Electronic Specifier Insights, the podcast for electronics engineers. I'm your host, Paige West. In today's episode, I speak with Piyush Sevalia, Executive Vice President for Marketing at SiTime. SiTime has recently announced the differential-ended SiT5977 Super TCXO, the newest member of the SiTime Elite RF family. So we speak about this product's features and its contribution to AI compute node efficiency and the reduction of energy consumption in data centers. We hope you enjoy this episode. Let's get started.
Electronic Specifier.
I'm pleased today to be joined by Piyush Sevalia, who is the Executive Vice President for Marketing at SiTime. So thank you very much for joining us. It's a pleasure to have you as our guest today. How are you? Are you well?
I'm well, thank you, and it's a pleasure to be on your podcast.
Great. So if you could start, please, just by introducing yourself and telling us a bit about your background.
Sure. So my name's Piyush Sevalia. I'm the EVP of Marketing at SiTime, and I have responsibility not just for marketing, but also for the business units that we have that are reporting into me, and therefore the revenue responsibility for that too. I've been in the semiconductor industry for almost 34 years now. And this is only my third startup, or a third company, which is a bit unusual for Silicon Valley. I kind of like to go into companies and help grow them. So I came to SiTime in 2008 when we were very little revenue, almost zero revenue at that time, and still in the process of building the technology and the products. And here we are at whatever the revenue will be for last year. We haven't announced that yet, but in the range of 200 million is what people expect of us, the analysts expect. And then on top of that, a market cap of almost 6 billion. So clearly the market expects that we will grow, and all these new product introductions that we do are in service of that.
Fantastic. So for our listeners who perhaps aren't as familiar with SiTime, give us a bit of a background into the company as well.
Sure. So actually, before I get into SiTime, a little bit of background on the timing industry. So we know that all modern electronics needs time as a reference, as a clock for anything inside the device to operate. I mean, when you have PCs running at several gigahertz, that's coming from the source of time, the time signal that's going into the processor. When you have Ethernet running at 400G, 800G, whatever the number might be, again, that is coming from timing. At the heart of this is timing. You need a clock signal, and a very good clock signal, to make sure that the systems operate correctly. Now, for the last 70, 80, 90 years, this clock signal was provided by quartz devices. So it was using quartz crystal technology. It's pretty good technology. It's got us this far. And that's what was the industry standard. Now, when SiTime was founded about 20 years ago, our vision was to change the technology from quartz crystal to silicon MEMS. And the reason for silicon, pretty much silicon, anything that it touches, whether it is any kind of electronic device that it touches, it basically takes over and becomes the incumbent, because silicon is a highly scalable technology. It's highly manufacturable. There's a huge amount of infrastructure out there, and it gives benefits such as more features, higher performance, lower power, things like that, smaller size, higher reliability. And so that's what happened. That's what we were founded with that vision. Now, fast forward to today, and basically what's going on is that electronics fundamentally is changing. Pretty much all electronics now is connected. Pretty much all electronics now has intelligence. And the intelligence is being pushed out closer and closer to the customer. Versus previously, it would have not been, the decisions would have been made in some central, whether it was a mainframe, whether it was a server, whatever it was. Now the intelligence is getting pushed out closer to the customer. And of course, there are just so many protocols out there. I mean, if you look at your cell phone and think of the number of wireless protocols in there, you've got the cellular protocol, you've got the Wi-Fi protocol, you've got the Bluetooth protocol, you've got NFC, In some cases, you have radar. There's just a lot more technology that we are packing into the same form factor. So these are the problems that we're trying to solve from a timing point of view. How do you make sure that performance increases? How do you make sure that connectivity is always on? How do you make sure that the intelligence is higher? You can do all the different tasks that we have to do. And how do you make sure that this works in the presence of all these different protocols that are in there? And so we basically coined the term precision timing, which is different than timing. And the point of precision timing is that it should allow electronics to operate because timing is the heartbeat. So it should allow electronics to operate and deliver all these values of higher performance, better and always on connectivity, better reliability, making the end devices more safer, things like that. And the timing should always be operating no matter what the environment. And so that's what we focus on. That's our value add to this whole industry. We focus on building devices that solve customer problems in the space of performance, in the space of connectivity, in the space of reliability, in the case of continuous operation and uptime. In all of these cases, that's what we try to solve. And that's our vision, is basically go focus on this, go solve this for the customer, and good things will happen.
Brilliant. Thank you for that. That was a great opening to the conversation. And the focus for today's podcast is going to be on a new product announcement that you guys have launched not that long ago, back in January. It's a new member of your Elite RF family. But before we dive into that, can you start by explaining the role of precision timing in the context of AI data centers and why it's such a critical component for their efficiency?
Sure. So data center, an AI data center has many different types of applications. You have GPUs, you have CPUs, you have servers on which these things reside. You have switches to route the traffic. You have top of the rack switches. You have within the rack inline switches. You have optical modules that are used to transmit Ethernet at very high bandwidth. You have active electrical cables. You have active optical cables. You have GPU switches. So there's just and NIC cards, network interface cards. So there's just a whole bunch of infrastructure that's going into the AI data center. So where does timing play a role? Obviously, for all of this electronics to operate, you're going to have good timing. But the places where we will make a real difference could be more on the networking side. In the data center, more of our business comes from networking than it comes from the processing part or the computing part of the data center. Why? Because the speeds for networking are constantly increasing. 2 years ago, the mainstream data throughput was 400 gigabits per second Ethernet. Today, it's 800 gigabits per second. In a couple of years, it's going to be 1.6 terabits per second. For these kind of speeds, you need to make sure the timing is very accurate. It's very reliable. So that's one place where we play a role. And if you think about it, any one of these applications goes down and suddenly you are impacting the whole data center. I mean, we heard numbers like, one of the CSPs, the cloud service providers, for every 24 hours that the data center is down, they lose like $2.4 million in revenue. So literally uptime has to be very, very good. And a data center is a noisy environment with all these things bouncing around. There's a lot of electrical noise. There's a lot of vibration going on. And so for those kind of things, we basically offer the benefit of higher environmental resilience. So that's the basic role of timing. Now, when you take a specific application like a network interface card, actually, before we get into that, let's step back a little bit too. One of the other requirements for a data center is that all of these different applications need to be synchronized in time, meaning they should be within a certain window of time accuracy to each other. And why is that important? Because if you think about it, in a data center with several clusters, you're going to take a training task and you're going to break it up across all these different processors. And then once each of the processor has finished with the task, you're going to reassemble it. Well, think about it when you're going to break it up. And then when you're going to reassemble it, if the timing is different between the breakup and the reassembly, now suddenly you have a problem. Secondly, when you break it up and you're trying to keep the pipe to the GPU full, if the GPU and the place where it's distributed are on different times, you're never going to know when the GPU is idle. I mean, there was a study done out there which said that almost GPUs are idle almost 30 to 50% of the time during various training tasks. And so to maximize the utilization of the GPUs, you need to make sure that you're queuing up your jobs correctly and with the best time efficiency. That's where timing comes into play. So you need synchronization, time synchronization to make sure that you're doing all this efficiently. And so if you take a NIC card, for example, a network interface card, uh, that our devices in the presence of these disturbers like power supply noise, like vibration, like airflow, things like that, we deliver 3x better synchronization. We deliver 4x better reliability than our competitors. And because of these two reasons, we increase the uptime of the system. Not just that, but we make sure that the tasks can be more efficiently queued because the synchronization is better. And so that's how we help efficiency in data centers.
Fantastic. Let's bring this new product of yours into the conversation, which is the SiT 5977 Super TCXO. It's been described as enabling tighter synchronization and more efficient architectures. So can you elaborate on what makes this timing solution so unique compared to alternatives?
So the uniqueness comes from how we built the device. So our device, many people say, well, it's just a timing device, but there's a hell of a lot of technology that goes into the timing device. So at the heart of this is our MEMS technology, silicon MEMS technology. MEMS is microelectromechanical systems. You're literally building machines inside a silicon die. And so that we are used to things inside silicon moving, electrons moving and all that stuff. Well, here, actually the structure is moving. And so you've seen MEMS in a variety of different applications, gyroscopes, accelerometers, airbag sensors, things like that. We're using that for timing. And our MEMS is much, much smaller than an equivalent quartz crystal, and it has much less mass. So laws of physics, right? Force is equal to mass times acceleration. If the acceleration, which is some kind of mechanical stress, whether it's vibration, whether it is shock, if the acceleration is the same, the smaller the mass, the less force couples onto your device. That's how we are so mechanically resilient, because our MEMS resonators are so much smaller. It's like a 0.6 by 0.6 millimeter die. Actually, it's a 0.5 by 0.5 millimeter die. It's pretty tiny. So that's one part of it. So that's how we get mechanical resilience. Then the other part is the analog. So we have our MEMS teams, we have our analog teams. And this is fundamentally different than how the quartz industry operates, where they are experts in precision machining. But the analog is usually outsourced to semiconductor companies. The fact that we have both departments inside the company and we're developing a product together allows us to basically co-optimize. So our analog takes into account the advantages of the MEMS and then designs the analog around that. And we make the analog resilient to, for example, rapid temperature changes. Because when temperature changes rapidly, the frequency is going to change. That's a characteristic of any frequency generation device, whether it's quartz or MEMS. We compensate for that through our analog, and we do it better. So that allows us to give you better resilience and airflow. Then what we do is basically, because the two devices are inside SiTime, the technology is inside SiTime, we basically also co-optimize how we're going to partition the design and then put it together to deliver the best performance. So literally, we are able to do in this device what is required from the quartz industry. You require two separate devices to do. And so we are 1/4 the size because we're doing it all inside the same device. There are two factors here. One is jitter, which is used for SerDes communications like Ethernet. And the second is stability, which is used for synchronization. And we deliver both from the same device versus the quartz devices where you have to use two separate devices. The fact that we are one-fourth the size of the competing solution allows the system designer to increase the size of their ASIC. They can do more processing. And that's how we help the system provider.
Hmm.
So not only do we bring the benefits of efficiency, but we also allow them to design higher performance systems because we've decreased the size of the timing components on the board, allowing them to pack more into their SoCs.
Fantastic. And the integration of digital control with precise tuning and the elimination of external LDOs seems quite a significant point. So can you explain how these features simplify AI system architecture and improve overall performance?
So first of all, because you're able to get your SoCs bigger, the NIC card SoCs bigger, you can have more ports supported from the same NIC card. So if your originally your NIC card was like 32 ports, now you can go up to 64 or 48, whatever your architecture desires. So that's how you get more. One way you get more efficient, more performance because you're now able to support more ports. Second, because you're expanding the size of the SoC silicon, you can actually have higher performance in there because you have more processing elements in there. So instead of working at 800G, you could actually go up to 1.6 terabits per second. So that's another way we are helping them. If you look at the synchronization aspect, the fact that we are 3x better in synchronization allows you to queue traffic a lot more efficiently than if you were not. It's kind of like the signaling on a railway line, right? I mean, if the railway line, the automated signaling has smaller error, the trains will be closer together without causing an accident. And that's what we end up doing. So that's how we get more efficiency out of the system through synchronization as well as higher performance.
And speaking of synchronization, how does the type of synchronization enable finer grained network telemetry? And why is that important for reliability and performance in AI operations?
Good question. So basically, network telemetry is about measuring the signals that are coming through the network and then taking action around that. So coming back to that point of 3x better synchronization, the fact that we are able to queue traffic a lot better means that you have finer grain resolution on the parameters of the traffic. So that's one way we help the system provider. The other way that we kind of help the system provider is we have some features in the device so you can fine tune the device. So think of your classic analog radio. You've got a coarse tuning knob, which gets you to the radio station you want. And then you've got a fine tuning knob that allows you to improve the signal to noise ratio so you get the best output. We have something similar built into our devices. So we have literally a digital control into our devices, which is kind of like that fine tuning knob, and allows you to get the most efficient the best synchronization leading to the most efficient data transfer. And that's how we basically help the system in this.
Hmm. And with AI training and inference becoming highly distributed processes, I'm interested to hear what challenges the SiT 5977 overcomes in achieving high bandwidth interconnects and reliable synchronization.
Yeah, so we talked about this whole move from 800G to 1.6 terabits per second. So there's two ways we solve the bandwidth problem. The fact is we're giving better jitter. I mean, think about the power supply lines that are in a data center. Because there's so many things bouncing around, because data is being transferred, the power supply typically has a lot of noise on the line. So the more immune you are to power supply noise, the better performance you can offer. Now, in the case of Ethernet, the spec that matters is something called jitter. It's basically how the rising edge of the clock moves compared to its ideal position, which when integrated over time or integrated over frequency, you have like period jitter or you have phase jitter. Those are the two terms that matter. The bottom line in Ethernet is that you got to have lower jitter. And you can have a spec. You can have a spec saying our jitter is 100 femtoseconds. But guess what? When you introduce noise on the power supply line, that 100 femtosecond spec may get blown out of the water because there's noise on the power supply, which is going to create more jitter coming out of the timing chip. We are more immune to power supply noise because we've designed our chips to be more immune for that. We have the analog expertise. So now what happens is that you're able to deliver the jitter that is required under all operating conditions. Doesn't matter how much power supply noise you have. So because the jitter is guaranteed to be below a certain number, you can meet the higher performance requirements. Not just that, but you're not going to introduce bit error rates because the jitter blew past your target. And we've heard this from customers who have used quartz devices that the jitter just goes up when there's power supply noise. We eliminate that. So that's how we help the performance. So that's one way of helping. That's just the raw bandwidth of the Ethernet. The second way is what I talked about from a synchronization point of view. The tighter the synchronization, the better the throughput. So that's another way we help.
And given all you've said, I think it's quite clear that the AI data center market is expected to grow quite rapidly, and I'll talk about some stats in a minute. But there's also significant concerns around energy consumption and carbon emissions. So I'm interested to hear how SiTime's solutions are addressing these sustainability challenges.
So I'll talk about it at a very basic level because there's a lot more work to be done on the whole energy consumption piece. And we're working on it. So that maybe at a future point, we'll talk in a lot more detail. But at a very basic level, the fact that we are combining two functions into the same timing device, good jitter as well as good stability, which would have required two separate devices in the past. That in itself is going to give us better power efficiency. Because if you're actually using two separate devices, you got to get the signal off one device into another device and then off the other device. And just getting the signals in and out of the chip consumes additional power. So the fact, in the case of quartz, you typically need a ultra stable TCXO, or for that matter, even an OCXO, an oven control device. In our case, we can do it with a DCXO. Now, an oven control device typically consumes a lot more power, typically 4 to 5 times the power of a TCXO. But because of the spec requirements, in the case of quartz, customers were using OCXOs and therefore consuming a lot more power than our TCXOs. So that's one way we help. The other way we help is just because in our TCXO, we have the jitter and the stability. You don't have to use a separate jitter cleaner device to clean up the signal for the Ethernet. And so therefore, the savings of that additional device and the functions that it performs, that saves power too. So we haven't done the math on all of this because there's many different options that the customer can use. But generally, these are the two places where we save power. Now, frankly, we're just scratching the surface here. There's so much more work that needs to be done. And we've got some pretty interesting ideas around this in terms of what we can do in the future. So that is something that we will talk about at a future date. But this is just the beginning, is what I call it.
Yeah, fantastic. Well, we'll have to bring you back at some point to talk about all these ideas.
Happy to.
So the data infrastructure market is currently valued at around $200 billion, and there's an expected 40.5% annual growth rate for AI workloads. Where do you see SiTime positioning itself in this evolving landscape? I mean, you've mentioned some ideas that we can talk about, at a later date. But I'm interested, where exactly do you position yourself in this market?
So first of all, I mean, we want to be, and to an extent, we're already achieving this, but we want to be the provider of choice for all the applications in a data center. So whether it is clocking for CPUs, GPUs, NIC cards, GPU switches, top of the rack switches, active electrical cables, active optical cables, whatever it might be, we want to be the timing provider of choice. And so in that sense, not only do we have a very compelling set of products today that solve specific problems, just like this 5977, We have a whole bunch of other products that are already designed into these systems and that we have been shipping for a while that solve specific customer problems. But not just that, but we have to evolve. We have to have a roadmap that supports the future 1.6 terabit per second standard, as well as a couple of years after that, probably going to 3.2 terabits per second, because the demand for this is pretty, some people have used the word insatiable out there, which is kind of a pretty strong word, but that's what they say. 40% CAGR is quite something. And so there is an aspect of innovating very, very quickly to meet the requirements of the market. For example, your jitter has to be half the value every 2 years. For example, basically your synchronization requirements today, we are 3x better. In 2-3 years, we might need to be 6-7x better. And so that rate of innovation is what we are focused on delivering. And so obviously we have roadmaps to support this, not just the raw increase in speed, but separately, how do we solve problems at the system level? How do we give better synchronization, for example? How do we change the architecture by making the devices maybe smaller, maybe getting more features in it, whatever it might be. So when we look at our roadmap and we develop the roadmap, we are actually looking at what problems we are solving for the customer in addition to the raw performance that is required. And so clearly we have to have that innovative roadmap, which we have. We are working on that and developing it. And you'll see a lot of new product introductions in the future around this. And then, of course, being very closely engaged with the architects at the silicon providers, the OEMs, as well as the cloud service providers, and making sure that we are working with them closely. And we made a reference to this every time we've talked about earnings, about how we are working with them to develop new products that solve specific problems in their systems. So that's what we do. Ultimately, it's all about solving the customer's problem and innovating so that you can do well and the customer also gets what they need.
Well, we're certainly looking forward to any new product introductions you're going to announce this year. But coming back to the 5977, for those who would like further information, what are the next steps? Where can they access samples? Where can they get additional information?
Best place is our website. It has all the information. We try to make our website very, very informative. So not only do we have the usual stuff, data sheets and models and things like that, but we also have an e-commerce section where you can order certain products. The 5977 may not be there yet, but it will be there shortly. So literally going to the website and getting all the information. And oh, by the way, if you don't have anything, start a chat session with someone and get them to basically help you out. We are very responsive on that. So I would ask your listeners to go to the website and start there.
Brilliant. And before we wrap up, is there anything else that you wanted to discuss? Any additional comments?
Just that for your listeners, keep SiTime in mind as the preferred timing provider for all things related to precision timing.
Fantastic. Well, it's been brilliant speaking with you. Thank you very much for your insights and for all the background into timing technology. It's been a learning path for me, so thank you.
Thank you, and thank you for having me.
You're very welcome.
Thank you for listening to this latest episode of Electronic Specifier Insights. Don't forget to subscribe to the series to keep up to date with our newest guests, and do share with fellow colleagues, friends and family who may be interested in the latest news from the electronics industry.
Electronic Specifier.